Day 1, Chapter 9, Introduction to Significance Tests. Confidence intervals are one of the two most common types of statistical inference. Use a confidence interval when your goal is to estimate a population parameter. That basically was the focus of Chapter 8. Now, moving on to Chapter 9. The second most common type of inference, called significant tests, has a different goal: to assess the evidence provided by data about some claim concerning a population. Well, what is a significance test? It is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population P or population mean mu. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree. In this chapter, we will learn the underlying logic of statistical tests, how to perform tests about population proportions and population means, and how these tests are connected to confidence intervals. So here's an example that lays the groundwork for the thought process behind this. I'll zoom in on this a little bit. That's pretty good. Suppose a basketball player claimed to be an 80% free throw shooter. To test this claim, we have him attempt 53 free throws. He makes 32 of them. His sample proportion of made shots is 32 out of 50, or 0.64. What can we conclude about the claim based on this sample data? We can use the software to simulate 400 sets of 50 shots, assuming the player really is an 80% shooter. Or we could do some type of hands-on manipulative simulation, or we could set up something with random number tables. For this particular simulation, they decided to use technology. You can say how strong the evidence against the player's claim is by giving a probability that he would make as few as 32 out of 50 free throws if he really makes 80% in the long run. The observed statistic is so unlikely that the actual parameter, P is equal to 0.8, that it gives convincing evidence that the player's claim is not true. So here is what happens in this particular set of data. In 400 sets of 50 shots, there are only 3 times when a shooter made as few as 0.64. So let's flesh out those ideas a little bit more. Okay, based on the evidence, we might conclude that the player's claim is incorrect. In reality, there are 2 possible explanations for the fact he only made 64% of his free throws. Okay, 1, the player's claim is correct. He really is an 80% free throw shooter, and by bad luck, a very unlikely outcome occurred. Or, number 2, the population proportion is actually less than 0.8, so the sample result is not an unlikely outcome. So the basic idea here is an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. So in this case here, 3 out of 50, is that considered significant evidence for that? All right. Now we're going to spend a great deal of time. How do you formally write one of these up? Now the things about the idea of setting up simulations and determining if an event was unlikely or an unusual event, we've been talking about this for quite a while in the class with different simulations that we've done. The reason why we've done that is to kind of lay the groundwork for what we're going to be accomplishing in Chapter 9, and it dominates a decent part of the rest of the class. AP rubrics are very, very specific in terms of how these significant tests need to be set up. very, very specific in terms of the vocabulary you use, in terms of the symbols you use. So what's going to be happening for a good chunk of the rest of the PowerPoint is going to be concentrating on what are those details that you need to have in place in order to be getting full credit for one of these guys. All right, so the first thing we're going to address, or the next thing we're going to address, is how do we set up our hypotheses? A significance test starts with a careful statement of the claims we want to compare. First claim is called the null hypothesis. Usually the null hypothesis is a statement of no difference. The claim we hope or suspect to be true instead of the null hypothesis is called the alternative hypothesis. So the symbols that we use here are H sub O for the null hypothesis and H sub A for the alternative hypotheses. Well, null hypothesis and alternative hypothesis, we are going to be using those terms pretty frequently. As I said, the ideas that we're going to be doing in this, or laying the groundwork for in this particular section, we're going to be using pretty much for the rest of the year. So we are going to refer to this as a ho and refer to this as a ha. Not exactly mathematically sound, and some may consider the ho to be a politically incorrect term to be using, depending on how you think of that term. But in terms of getting through this material without using long verbiage, ho and ha are what I'm going to refer to them as. So, going back to our free throw shooter example, this is what our ho and our ha would look like. The ho is that the true proportion of his free throws really is 0.8. Now we suspect that he's not necessarily telling the truth, and we would like to show through our data that the actual proportion is less than the 0.8. One of the things that you need to have set up when you do these in free response form is whatever the variable is here, which for this chapter is either going to be a p or a mu, you always have to specifically state what it is in this particular part of the write-up. All right, in general, this is what the structure is going to look like. In any significance test, the null hypothesis has the form your ho, the parameter of interest is equal to some particular value. The important thing is, or one of the important things to emphasize is, your ho always has an equal sign associated with it. Now, I always try to bring up how our textbook or AP could possibly be different from other resources, other textbooks that you go to. In some statistical scenarios, it's acceptable to have a less than or equal to or greater than or equal to with your ho. Your book in AP, every once in a while, will sneak one of these guys in, but for the most part, it tends to stick to the parameter equal to some particular value. Sometimes you will see this. All right. The alternative hypotheses, or your ha's, always are an inequality. It could be a greater than, a less than, or not equal to. All right, these guys are known as one-sided tests. This guy is known as a two-sided test. Sometimes they'll be referred to as directional. If it's a less than, that would be referred to as a left-handed test, or left-tailed test would be another term that you would see. This is a right-handed or a right-tailed test, a non-directional or two-tailed test. Those are other acceptable phrases that you can use for those guys there. All right, that just basically summarizes what I said here. A couple of important things here. Your hypotheses always refer to a population, not a sample. Be sure to state your ho and your ha in terms of population parameters. So for example, a p hat, you're not going to use in your ho. An x bar, you're not going to be using your ho. Those guys refer to samples, not populations. All right, for the types of problems that we do in this class, there's always going to be a p-value associated with your significance test. The null hypothesis, your ho, states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the null hypothesis is known as the p-value. So the probability computed assuming the Ho is true that the statistic would take on a value is at least as extreme as or more extreme as the one actually observed is called the p-value of the test. The smaller the p-value, the stronger the evidence against the Ho provided by the data. Small p-values are evidence against the Ho because they say that the observed result is unlikely to occur when the Ho is true. Large p-values fail to give evidence against the Ho because they say the observed result is likely to occur by chance when the Ho is true. And we've addressed this idea informally quite a bit. We're going to pause the video here for a moment. I'll be right back. All right, had a brief interruption there. Back to our PowerPoint. We are going to address an example that combines together the few concepts we've talked about so far. So here's our setting. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium. Is this true? So this is going to be our Ho and our Ha. The Ho, the mean is 1,300. One way to think about the Ho is it's the status quo. Things are as, in this case, like nationally assumed, nationally advertised. There is no difference. All these phrases kind of tweak which one matches best to the context, that they are getting enough calcium with 1,300. Now, what they're thinking here is teenagers aren't getting enough. So we want to show that their actual mean intake is less than 1,300. Now, the mu is a population parameter. Your Ho always has an equals. Your Ha is always a less than. Whatever this variable is here, which for now is either going to be a P or a mu, we have to specifically state what that is in context of the problem. Now, one thing that I notice is missing from this particular slide is if there's a unit associated with it, we should have a unit. We could either put the milligrams right here with each one, or maybe draw a little arrow in here, true mean daily intake in milligrams of teenagers. That most likely would be a detail that would end up costing you rubric points unless the milligrams was specifically stated somewhere else in the problem close to where we are. All right, so to test this, they ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data analysis reveals that the sample mean is 1198 and the standard deviation is 411. After checking that the conditions were met, researchers performed a significance test and obtained a p-value of 0.14, roughly. All right, so here's the idea. We're looking to show that something is less than 1,300. We got a sample mean of 1198. Now, is that a statistically significant difference, or can we just attribute it to chance variation? In this case, the context would be the students that were chosen. Okay, the two things that usually this is revolving around is this small enough or different enough from that, in combination with is 20 large enough of a sample size. The further this is away from there, in combination with the more or the bigger of the sample size, the stronger that evidence builds into this p-value. And those are details we're going to get to later in the chapter. Okay, so what they're asking us to do here, explain what it would mean for the null hypothesis to be true in this setting. In this setting, your Ho, mu is equal to 1,300, states that the mean daily calcium intake in a population of teenagers is 1,300 milligrams. If the HO is true, that means that teenagers are on average getting enough calcium. Okay, interpret the p-value in context. Okay, assuming that the mean daily calcium intake in a teen population is 1,300, there is a 0.14 probability of getting a sample mean of 1198 milligrams or less just by chance in a random sample of 20 teens. So we're going to flesh out a couple more details in interpreting a p-value, but basically, in very rough terms, it's assuming that the HO is true, what's the probability of getting results at least as extreme as these? All right. Next thing is, how do we write up our conclusion to these guys? The final step in performing the significance test is to draw a conclusion about the competing claims you were testing. We will make one of two decisions based on the strength of evidence against the null hypothesis, which means that indirectly you're in favor of the alternative hypothesis. We're either rejecting our HO or we're failing to reject the HO. If our sample is too unlikely to have happened by chance, assuming the HO is true, then we reject it. Otherwise, we fail to reject it. A fail to reject HO decision in a significance test doesn't mean that the HO is true. For example, you should never accept your HO or use language implying that the HO is true. It's kind of like if you're tried for a crime and you're found not guilty, it doesn't necessarily mean that you're innocent. It just means that there wasn't enough evidence to convict you. So connecting that to this world right here, it doesn't necessarily mean we have enough evidence to accept the HO, which we don't have enough evidence to reject it. Okay, in a nutshell, our conclusion in the significance test comes down to this. If you have a small p-value, you're rejecting the HO, and then you conclude that the HA is true in whatever context. If your p-value is large, you fail to reject the HO, and you can't conclude whatever the HA is. Right, there is no rule for how small a p-value we should require in order to reject the HO. Okay, the default that we've talked about many times in this class is the 0.05. Okay, that's the most common one, but it could be higher, it could be lower, and it's the one that you should go with in terms of the safest way to get full credit. If an alpha level or a significance level, they mean the same thing, which we're going to talk about in a second. If it's not given, that's the one you want to assume you're going to go with. Okay, it's a matter of judgment. It depends on the specific circumstances. But we can compare the p-value with a fixed value that we regard as decisive, called the significance level. And we write that as alpha. Some students have referred to that, as politically incorrect as it may be, calling it Jesus fish. I would prefer that we didn't go with that term, but if that helps you remember how to draw it, I don't have any problems with that. When our p-value is less than our chosen alpha, we say that the result is statistically significant. Okay, so if the p-value is smaller than the alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis, the HO, and conclude there is convincing evidence in favor of the alternative hypothesis, or HA. Okay, when we use a fixed level of significance to draw a conclusion in the significance test, okay, so this just fleshes out a little bit more detail than what we saw last slide. Instead of saying a small p-value, the p-value is less than the alpha. If the p-value is greater than or equal to the alpha, then we fail to reject. All right, so let's take a look at that idea in the context of an example. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced they really do last longer. Based on years of experience, the company knows that the regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. The mean for this sample is 33.9. Okay, significance test is performed using the hypotheses. So the HO is the status quo, things are as usual, the baseline we're going to compare things to. That the true mean is 30 hours, that's the industry standard at this particular moment. We would like to show that our new batteries last more than 30 hours. Whatever variable you use here, you have to specifically define it, where mu is the true mean lifetime of the new deluxe AAA batteries. And what else do we have to address here? Oh, the HO, make sure you have an equals. The HA is an inequality that doesn't include an equals. Okay, the resulting p-value is 0.0276. So what conclusion can you make at the alpha level of 0.05? Since the p-value of 0.0276 is less than the alpha of 0.05, the sample result is statistically significant at the 5% level. We have sufficient evidence to reject the HO and conclude that the company's deluxe AAA batteries last longer than 30 hours on average. So, if the p-value is less than the alpha level, we reject the HO, we have evidence to support the HA. What if our alpha level was 0.01 instead of 0.05? Okay, now, since the p-value 0.0276 is greater than the alpha level, the sample result is not statistically significant at the 1% level. We do not have enough evidence to reject the HO. In this case, therefore, we cannot conclude that the deluxe AAA batteries last longer than 30 hours on average. When we make a decision based on a significance test, meaning we reject or we fail to reject, we hope our decision is correct, but in fact may be wrong. We really have no way of knowing. If we did, we wouldn't have done the test in the first place. Sometimes we get a rare freak sample and reject a null when it's actually true. We may have failed to reject when it truly is a false claim. So what we're going to do is classify what can go wrong here. If we reject the HO when the HO is true, it means we commit a type 1 error. If we fail to reject the HO when the HA is true, we commit a type 2 error. And one quick thing that we can do as a memory trick, fail to reject is a type 2 error. So that can help us organize this information. So there's 4 things that can happen when we do a significance test. In your significance test, your HO could be true. And if we fail to reject it, it means the test went well. Your HO could be false, which means if we reject the HO, things went well. And you could think of it as the HO is false, the HA is true. In terms of AP questions, they use both of those ways of describing it. Now, other things that can happen. Your HO could be true, and you actually reject it. That would be a type 1 error. Your HO could be false, and you fail to reject it. That could be a type 2 error. Fail to reject, type 2 error. Now, while we can never know if we're making a type 1 or a type 2 error, we can calculate the probability of making an error. Okay, the probability of making a type 1 error is your alpha level. So if your alpha level is 0.05, the probability of rejecting a null when in fact it is true is 5%. Okay, the type 2 error probability stuff, turns out that's a little bit more complicated, actually a lot more complicated. We're not going to go into that in a whole ton of detail in this class. That kind of sneaks above and beyond the context of what we need to know for AP purposes, but we are going to address this in more detail in a future lesson. All right, so back to our battery example. All right, everything is still the same all the way up to here. Now, what they're asking us to do is to describe a type 1 error in this setting, describe a type 2 error in this setting, and what would be the consequences of each. Okay, this is a very, 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 and we'll throw 2 more in, very, very common AP question. And you'll see this both in pre-response and multiple choice form. As far as the stuff we do in this chapter, it's a pretty big deal in terms of you're guaranteed to see this on the AP exam. All right, so describe a type 1 error in this setting, and then what are the consequences of making this error. Okay, the way that you want to word this is make your first statement the generic, you know what the definition of making a type 1 error is. A type 1 error is rejecting a null hypothesis when it is in fact true. Okay, that is a generic statement that applies to all type 1 errors. Now specifically, what does that mean in this problem? It means we found convincing evidence that all new batteries last longer than 30 hours on average, when in reality their true mean lifetime is 30. Okay, a possible consequence of this error would be that the company spends extra money to produce these batteries when they aren't any better or older than a cheaper type. So, type 1 error is rejecting the null hypothesis when it's in fact true. So, it is true that there is no difference in the old batteries, in new batteries and the old batteries. But we found evidence that it is. So, we found false evidence that they really do last longer. So the consequence of this is the company would invest whatever money it would invest in to make these new batteries, and the new batteries aren't any better than older ones. All right, what would a type 2 error mean in this setting, and what are the consequences? All right, the way that you would want to word this is make your first statement the generic statement. You want to show the reader of the question, you know the definition of what a type 2 error is. A type 2 error is failing to reject the null hypothesis when the HA is true. Okay, in the context of this problem, it means convincing evidence was found that the new batteries do not last longer than 30 hours on average, when in reality their true mean lifetime is greater than 30. Possible consequence of a type 2 error would be the company would not produce the new batteries even though that they were better. So, a little bit more detail up here. A type 2 error is failing to reject the null hypothesis when the HA is true. So in reality, this is true and this is false. The correct decision would have been to reject this and have evidence for that. But we failed to reject type 2 error. So we failed to recognize as a company that we actually produce better batteries. So the consequence here is that the company wouldn't be producing these new batteries even though they were better. All right, this PowerPoint contains another example of the type 1, type 2 error. In the interest of time, I'm not going to go over these in this particular video. You can read those on your own. We're going to stop right here as far as this particular lesson goes.